Hello everyone, welcome back to the course on Trustworthy machine learning. In this lecture, we'll talk about confidential, private, and robust collaborative learning. This is a continuation of the previous lecture that discussed the federated learning and its vulnerabilities to various attacks. Here we will focus on how to create frameworks for collaboration that can defend against the adversaries that Francesca discussed last time. Collaboration is a key component of learning for both humans and machines. Let us imagine that there is a user Bob who types in his smartphone "my credit card." Next time when Bob types the words "my credit," we'd like to suggest to Bob the word "card." Locally, on Bob's smartphone, we train a model that predicts the next most likely word. Such information about word sequences is also collected and used to train local models on other users' devices. Then these models that we train locally on users' devices are sent to a central server that combines the received model updates into a shared central model. Then the updated shared models are returned back to the client's devices for further local training. Next time when Bob types "my credit," the keyboard suggests the next words being not only card but also score, or even an icon of a credit card. The predicted words by the keyboard are based on the next words used by many different users, not only by Bob. What Bob types or selects from suggested predictions is further fed back to the local model to improve the next word prediction service. This type of collaborative learning is called federated learning. More systematically, there is a central server that sends a model to clients. Next, each client trains the model locally on its own private data and sends gradients, new model parameters, or other forms of updates to the central server. The central server aggregates the shared updates into a new global shared model. Then again, this new shared model is sent to the clients, and we iterate through this process many times. So this is just a recap of the previous lecture on federated learning. Now, let's talk a bit more broadly about where it is deployed. So apart from the next word prediction in virtual keyboards on our smartphones, it's also used, for example, by Apple to improve the voice recognition system, such as Siri. Collaborative learning is used also by many hospitals to enable collaboration without revealing the patient's private data. The healthcare domain can take advantage of the abundance of data collected on our smartphones about our heart rate, step count, or activity type, such as our workouts. Finally, collaborative learning is used in the financial domain to train models for fraud detection or loan application decisions. However, the question is, if Bob types some information on his smartphone that might be sensitive, for example, "my credit card is," could someone steal this information from his device? In the previous lecture, Francesca showed that federated learning is not private. We can steal individual training samples from the updates that clients send back to the server. Here, the original text is what Bob typed on his smartphone. Then we can extract exactly the same text. Extraction is perfect. There is no reconstruction error. The attack also works for other domains, such as vision, where users train the shared model on their private images, shown in the first row. And we are able to reconstruct these images without any flaw. The stolen images are shown in the second row. So now let's take a step back and ask, where is the main problem? In traditional centralized machine learning, a central model is trained on all available data stored in the central server. So this is the standard way how probably most of you currently trains ML models. In federated learning, the local model is trained on local client's private data. The data that is in a plain form never leaves the client's devices. The local devices send model updates to the central server, which then updates the shared model, which is then sent back to the clients. However, what we learned is that the main issue is that the central server might act maliciously and easily extract individual data points. Thus, to tackle the problem, we want to remove the central server that orchestrates the whole collaboration and enable fully decentralized architecture where clients can communicate between each other. Other way how to call this architecture is called peer-to-peer. So peers are these clients who wishes to collaborate in this collaborative learning protocol. Current collaborative learning approaches are vulnerable to both server attacks and client attacks. The clients are denoted as C with data D in this diagram on the right hand side. We already saw that malicious servers may attempt to, for example, reconstruct individual data points from the client's updates, thus breaking the data confidentiality. And how to perform that, we learned in the previous lecture that this can be achieved by modifying model parameters or colluding with other parties. Second, also the malicious server can inappropriately change the shared model by, for example, omitting updates from selected clients, adding bogus updates, or otherwise altering the global model updates. If we talk about now, focus now on malicious clients, they may attempt to, for example, lower the quality of the trained model by sending distorted model updates. So this may take the form of both intentional model poisoning attacks and then, for example, unintentional problems such as errors in computation and skewed or incorrect local data sets. Clients may also attempt to steal information about the other's peers' data. So they can just wish to break confidentiality of the other clients in the collaboration, and they just want to steal their data by colluding with maybe other malicious parties or clients and sharing transcripts of the protocol execution, meaning that two parties or more can just share what they compute as a gradient, and then through this sharing we can infer what were the, for example, gradients of other collaborating parties. So now we can analyze an example of an attack from malicious client. So this is a relatively successful attack if we consider that attacker can try to break this protocol through many iterations. So we have the red star in the middle, and this red star is the true mean of the weights in all clients. The blue dots are weights in the clients after single training round. Intuitively, the values of the correct clients are spread symmetrically around the mean, and the extremes there are clients that can push strongly to the direction of an attacker. So similar number of clients push to the opposite directions. By now crafting clients by the adversary between the mean and the supporters, the malicious clients will be closer to the mean than the opposers one on the other side of this red star. So this makes most defenses against malicious clients to remove the non-malicious opposer workers, while choosing these workers that are malicious and then retaining them in the protocol. So this ensures that these Byzantine workers, so these malicious workers, can shift the mean of the final weights. So the variance of the clients around the mean is large enough for this effect to be meaningful after many iterations. So what we see here in this malicious client's approach to attack the protocol is that they act through many iterations of the protocol, and they place these malicious updates to the shared model in a way that avoids detection by many of the algorithms that are constructed to robustly aggregate many weights from many clients. Current collaborative learning approaches are vulnerable to both these clients who act, for example, as this little is enough attack, and server that can be malicious and change the models that are shared to the collaborating parties. So what we really want is to have a collaborative learning protocol that tackles these both vulnerabilities. So a protocol that is robust against malicious clients and at the same time also robust to malicious servers. So let's first talk about how we can provide robust aggregation against malicious clients. There are a few robust aggregation algorithms proposed. So we assume that we have n clients with model weights m sub 1, m sub 2, m sub n, and we want to robustly compute the output which is shared model weight, in this case v. So instead of using the standard mean of the model weights, we can simply use the more robust statistics and replace, in this case, mean with median. So this was proposed to be done on the coordinate level. Thus, per each coordinate, we compute the median value. Another popular approach was called RFA, that stands for Robust Federated Averaging. It's also known as simply geometric median. So here, in this algorithm, to robustly aggregate the updates from the clients, we perform the optimization to find V, the output from the aggregation, that fulfills this argmin. So this argmin is that we want to have a sum over this difference between V and M sub I, where M sub I is just an update from a client I, and we want to minimize this sum. So we want to find the minimum value of V that fulfills this sum. Finally, one of the most popular robust aggregation algorithms was CRAM. So CRAM tries to select a point M sub I, which is closest to the mean, after excluding fraction, some delta n plus 2, farthest away points. So suppose that S is a set of these clients of size at least n minus delta n minus 2, and then CRAM computes the M sub I by selecting the set S that has at least this number of n minus delta n minus 2 points for these clients, and minimizes the sum, which expresses the distance between weights m. So to just give more intuition for the CRAM, the idea is that ultimately we want to identify who are the malicious clients and exclude them from our aggregation. So here, this set S is supposed to be this set with benign clients, the ones that do not modify the weights maliciously to, for example, break the protocol. And we want to choose this subset of clients S of specific size that gives us the smallest value of one of the weights, so that we can return this weight. So this is kind of like the median weight. We can think about that in this way, from all the weights that are provided by the collaborating clients. So CRAM was one of the very first, but also one of the most famous protocols, because it has this very intuitive notion of excluding malicious clients. However, it was shown that the aggregation rule, which is oblivious to the past, meaning that aggregation rule like CRAM that does not really consider each iteration and what was happening, for example, in the previous iterations, does not converge to the optimum and retains a non-zero error even after infinite time steps. So this means that with CRAM we cannot really prevent against attacks such as Ali, a little is enough. So to overcome this issue, it was shown that the robust aggregation has to perform clipping and compute weights using momentum. So this is one of the ways how we can tackle the problem of the malicious clients that act through the many iterations of the algorithm. So first, the clipping operation is robust to the distribution of the gradient noise, and the clipping is very scalable, requiring only O of n computation and communication rounds. This is really much cheaper than the method from the previous slides, for example, CRAM. So this is standard clipping in the sense that we want to just limit how much influence a given client has on the final shared model. And second aspect here is that the time-coupled attacks like Ali can be easily circumvented with the computation of the aggregation with momentum. So this is something that we discussed in the previous lecture, that we aggregate the weights using the momentum, and momentum averages the updates of each client over time, reducing the variance of the good clients and exposing the time-coupled perturbations. So here we present the algorithm, and then in the first line we have n model weights. Each weight is done as m, and we have n clients. We also have the clipping threshold tau. The final output value should be v, and we have L training rounds for the collaborative learning. We start from round L, and the v being the average of the m values. For each iteration, we clip each model update, m sub I minus v, with the clipping norm tau. Then we simply aggregate the updates to return this expected value v. Eventually, we also incorporate the momentum. So the momentum is incorporated on the client side, here also called a worker. At every time step, training round t greater than 1, the server sends the worker's parameters x sub t minus 1 from the previous round, and each good worker sends back m sub I computed with momentum beta. And then we can set this beta, for example, to be 0.99. So here we want to ensure that the clients, they have this updates with some momentum, and this is quite large weight 0.99 to ensure that the clients are not with too much variance. The workers communicate their momentum vector to the server instead of the stochastic gradients directly, since they have a much smaller variance. And then malicious workers may send arbitrarily vectors to the server. The server then uses the centered clipping to robustly aggregate the updates. So now we can summarize the robust aggregation with a single server using this template. So we organize the aggregation algorithms in terms of three functions. The first function is fc, it's f upper C. This represents the computation of client updates based on local data, so the private data that client has, also the state of the client, for example, what is the learning rate, and then so on and so forth, and also the global parameters, in this case W. So W is just a global shared model. And the client returns update U sub I. Next, in the function f to the power of p, we do preprocessing. So this is computed on the server side, and for the centered clipping, the step involves, for example, the update clipping. And then here you have to note that the momentum was done on the client side. So this states for centered clipping on the client side. And finally, in the f to the power of r function, we compute the final update. And the server combines the preprocessed local updates into a global model update W, and then returns it back to the client for the next round of computation. And here we also have to note that the server computes this W using robust aggregation algorithms such as centered clipping, right? So in this case, if we have the processing steps that do momentum and then do the clipping, then the server just aggregates, in this case, just averages all the values that were obtained from the collaborating parties. However, centered clipping with momentum is not enough against malicious servers. So we have to ensure that malicious server cannot change the protocol and easily recover users' data. So here, to provide the protection, we need to use the cryptographic tools. This will allow us to lift the protocol to the peer-to-peer setting where clients or servers can act maliciously. The goal is to obtain a robust and actively secure serverless collaborative learning. The first cryptographic tool used in decentralized collaborative learning is MPC. MPC stands for Secure Multi-Party Computation, and here instead of having a single server, the clients can jointly compute the update. We will discuss MPC very soon. And then additionally, we don't want to force all the clients to jointly compute the update. We create an aggregation committee, which is a subset of the clients. So the committee is responsible for the aggregation of updates from all the clients. The size of the committee depends on how many clients we have and also how many of them might be malicious. To ensure security in the malicious case, we need the aggregation committee to have an honest majority, except with negligible probability, and usually the probability is very low, for example 2 to the power of minus 40. So to give you intuition, if we have, let's say, 100 clients and want to ensure security for the centered clipping momentum aggregation algorithm, then the committee size has to be of 46 clients. So now we have to delve deeper into the topic of cryptographic tools, and I will discuss a few of them that we will then use to provide the collaborative learning that is robust, private, and confidential. So let me give you a simple explanation of how the secure multi-party computation, in short MPC, works. So this cryptographic protocol is used to jointly compute a function over some inputs while keeping those inputs private. So this protocol distributes computation across multiple parties. And no individual party can see the other party's data. So now let's consider that we want to compute an average salary of 3 employees, Alice, Bob, and Carol. But these employees do not want to reveal their individual salaries. So in this case, behind the scenes, we know that Alice earns 100K, Bob earns 200K, and Carol earns 300K. How much they earn is not visible to anyone. It is only to illustrate this MPC, how it works behind the scenes. And now, once you have this setup, we want to compute what's the average salary of these 3 workers, Alice, Bob, and Carol. So in the first step, we generate random shares. A given salary, for example 100K for Alice, is split randomly into 3 shares, 50, 30, and 20. And this is split such that the added shares give the salary for Alice, which is 100K. This is done for each person. So for example, Bob has shares minus 80, 100, and 180. Carol generates shares 0, 350, and minus 50. So note that if you, for example, receive one of the shares from Carol, let's say being 0, of course you have no idea what's the Carol's salary. However, if you are able to get all of these 3 shares, then you might just sum them up and compute 300, which actually is exactly the Carol's salary. So you want to avoid that a single party gets all of these 3 shares. So what we do in the second step is that we do secret sharing. So for example, Alice keeps the secret share 50, which means that if Alice keeps the secret share 50 locally, then no one else can really figure out what's her salary because she only shared 30-20, but you need also this 50 to find out that actually Alice earns 100K. So Alice keeps the secret share 50 for herself and then sends 30 to Bob and 20 to Carol. Similarly, Bob and Carol also send 2 out of their 3 shares to other parties. And then in the last step, each person locally adds their final shares. So here you have to know that we just compute the sum of the shares that were given by other parties, these 2 shares, plus my own share, for example, as an Alice. So Alice has to sum 50 minus 80 and 0, which gives her minus 30. And the same procedure is done by each collaborating party, in this case by Bob and by Carol. So then we recombine all the results. So we add minus 30, 480 and 150, and this sum gives us 600. And then, because we had the 3 clients in the protocol, the average salary is 200. And this ends this secure multi-party computation, where we are able to compute the mean salary without revealing to any collaborating parties what is my own salary. Okay. Another cryptographic tool that we need in collaborative learning is called homomorphic encryption. The key feature is that it allows us to perform operations on encrypted data. For example, for inputs x and y and the function f to be computed, we define encryption and decryption functions. So in words, what's happening here is that we encrypt input values x and y and then compute the function f. It is equivalent to computing the function f on x and y and then encrypting the output. In neural networks, we need the function f to represent addition and multiplication for example, feed-forward layers or convolutional layers. So when we add encrypted x and encrypted y, we obtain encrypted x and y. You can also multiply these two encrypted values, x and y, to obtain encrypted x times y. To give more examples and some more explanation, apart from adding encrypted x and encrypted y to obtain encrypted x plus y, you can also take plain y, meaning unencrypted, then add encrypted x with unencrypted y to obtain encrypted x plus y. You can also multiply two encrypted values, x and y, to obtain encrypted x times y. For the multiplication, if we assume that the values are encrypted using, let's say, RSA, public key, an encrypted message x is obtained by taking x to the power of e modulo n. Then, when we multiply encrypted x by encrypted y to get xy, the power of e modulo n, this gives us encrypted x times y. Here we can formally define how we do the secret sharing. So secret sharing refers to the methods for distributing a secret among a group of people, or in this case for our collaborative learning, this is a secret that is shared among collaborating clients. And we want to do it in a way that no individual party holds any information about the secret. But when sufficient number of individuals, for example, we have enough of these parties that jointly want to compute the secret, then the secret might be reconstructed. So first we select binary number x of any length. So this is our secret that is expressed as this binary value. And then in our secret sharing, we just compute the values using exclusive OR operations. There are many different ways how we can deal with these computations for secret sharing, but this is one of the most intuitive ones. So the task is to split a secret x into shares x sub 1, x sub 2, and x sub 3. The procedure is to pick random numbers x sub 1 and x sub 2. Then we compute x sub 3 by doing exclusive OR of x with x1 and x2, where x is our secret. So in this case, this secret x remains indeed secret, meaning not revealed to anyone, until 3 of these shares, x1, x2, and x3, are combined. Here we also have a simple example in Python. So we select 4 as being value for x1, then x2 has value 5. Our secret is set to be 13. So x is set to be 13. We compute x3 by doing the exclusive OR between x1, x2, and x. So x3 in this case is computed as being 12. Then after the exclusive OR between the shares x1, x2 and x3, we can obtain the secret 13. And these operations can be easily done in Python, so you can just take this code and see that it indeed works. You can also do the homomorphic addition with another secret y. So here the secret y is divided into 3 shares, y1, y2 and y3. Each client adds the respective shares x sub I and y sub I. So for example, if this is client number 2, then the client number 2 adds x sub 2 with y sub 2. And the final output is the exclusive OR of the secrets x and y. Secret sharing is also used in secure machine learning to compute linear functions of secrets. Okay, another very important cryptographic tool that we actually use in collaborative learning is zero knowledge proof. So there is a very well-known story presenting the fundamental ideas of zero knowledge proofs. And then the story goes like that. So we have the 2 parties in our zero knowledge proof, and one party is Alice, which is who is a prover, and also we have another party that is Bob, who is a verifier of the Alice secret. So Alice wants to prove to Bob that Alice has some secret. So in this case, the secret is that a word that can open the magic door. So here we have this labyrinth, this tunnel with entrance A and entrance B, and we have magic door that is in the middle of this tunnel. And Alice wants to prove to Bob that she has the secret word to open the magic door in this tunnel. So she randomly selects entrance A or B, while Bob is not allowed to see which entrance is taken by Alice. Then Bob selects the entrance by which he wants Alice to return. In this case, Bob selects the entrance B. Providing Alice knows the magic word, she opens the magic door. And then she returns along the desired path, in this case, path B. So Alice could also choose entrance B at the very beginning, and then she would not have to know the secret to come back through the entrance B. To ensure that Alice really knows the secret, this procedure can be repeated many times, and each time Bob randomly chooses the entrance, either A or B. So, given that, we can now use these cryptographic tools and then construct this robust and actively secure serverless peer-to-peer collaborative learning that is extension of federated learning. So the protocol that is robust against malicious clients and servers. In the first step, what is done is that the clients randomly select the aggregation committee C. Then each client computes the local update U sub I in this second step. And this is done also taking into account local private data in each client, the state in each client, for example, learning rate or any other parameter, and also the global parameters for the whole collaboration, which is this vector W. Next, in the third step, additionally, each client does some pre-processing. So this was, for example, in centered clipping, was the clipping of this gradient. After this, in the fourth step, each client P sub I divides the computed gradient V sub I into shares and sends them to the members of the aggregation committee C. Then each client in the fifth step proves to the committee that the V sub I was correctly computed started from some U sub I. So here we use zero knowledge proof, but in the distributed setting because we have many committee members, so we have to prove that to many of these peers in the committee. Then, in the final step, the committee C does the robust aggregation and computes the final shared weights W. The W is then sent back to all the clients. Next, we will add the privacy to the collaborative learning protocol, and we now move from the robust federated learning to confidential and private collaboration, which is also called Capsi. So, secure and actively robust peer-to-peer collaborative learning was able to provide robustness against malicious clients and servers. However, it does not provide privacy guarantees that the private data in the clients do not leak the information about this private data to other collaborating parties. To further provide privacy, we will minimize the amount of exchange information, and instead of returning model updates or parameters from each client, we will operate on encrypted data and labels. So, to give you an intuition of why this is really relevant, let me provide you this scenario. This is based on the collaborative learning in the medical domain. So we imagine that there is a new patient who comes to a hospital. The doctor has not had such a case before and is not confident about his or her diagnosis, so wishes to consult with other hospitals or doctors. The doctor sends the chest X-ray of this new patient to other hospitals. These hospitals label the X-ray using their machine learning models, and then we aggregate the results to agree on a single most probable disease. Intuitively, what we achieve is an analog of a doctor querying colleagues for a second opinion on a difficult diagnosis. However, there are two main issues here. First, the answering hospitals do not want the liability for managing the private data about the new patient, and the patient would have to allow us to send his or her data to all of these hospitals, which is a lot of paperwork. Confidentiality means that the data is protected from the unauthorized access. The second problem is that the answering hospitals have to prevent others from inferring anything about their own private data. So this is the data on which these hospitals trained their own machine learning models. So the question is how we can solve these two problems. So now I will explain the second decentralized collaborative learning protocol, and this is called Capsi, which stands for confidential and private collaboration, that does not rely on a central party that orchestrates the whole protocol. So here let us imagine that we have a user, in this case again Bob, who has some unlabeled data. Then we encrypt Bob's data and send them to other collaborating parties. Then these parties do inference on Bob's encrypted data. Then we aggregate the predicted labels and release the final prediction in a private manner to Bob to improve his local model. More generally, in Capsi, this collaborative protocol, any collaborating party can act as a querying party or an answering party. A querying party sends data samples to be labeled to the answering parties, and we encrypt the queries and do private inference using machine learning models from the answering parties. Next, we aggregate labels instead of gradients to prevent leakage of the training data in the answering parties. And also here we use differential privacy, like the Pate framework, to aggregate the labels returned from the answering parties to prevent leakage of training data from answering parties to the querying party. For the inference on encrypted data in Capsi, we use both of these cryptographic tools, homomorphic encryption and secure multi-party computation. So again, as we discussed, homomorphic encryption is a form of encryption that allows us to operate on encrypted data, and here it is used in ML models to compute, for example, feed-forward networks or convolution operation. And then the second ingredient is secure multi-party computation that we described in the previous slides, which is a form of encrypted computation that enables multiple parties to compute a joint function without learning anything about the other party's data. So here we use MPC to compute nonlinear layers, such as in neural networks, for example, ReLU activation function. Next, in Capsi, we use differential privacy, as in the Pate framework, to aggregate the labels returned from the answering parties. This prevents data leakage from answering parties, and here we have to remember that in Capsi we operate on labels instead of gradients. So to release the labels to the querying party, we use the Pate framework. Pate aggregates labels from the answering parties to create a histogram. For example, if we have a binary classification task to decide if a given patient is healthy or has a cancer, the labels from the answering parties create a histogram with the number of votes per class. Then, for differential privacy, we add Gaussian noise to vote counts. Finally, we take the argmax of the histogram and return the label, in this case being healthy. So in Capsi, we use the third trusted party called Privacy Guardian that is responsible for adding Gaussian noise. So this party ensures that we add the required noise, and note that if one of the answering parties does not add the noise, then you cannot satisfy the required privacy guarantees. Now let me walk you through the Capsi protocol step by step. The goal is to label the new data item, here called a query. In step 1a, the querying party sends the encrypted query Q to each answering party. And we use homomorphic encryption to encrypt this query Q. You can think about query Q as being, let's say, this chest X-ray of a new patient. The answering parties do private inference on the encrypted query Q. Since the input is encrypted, also the results, so the output from the neural network, is also encrypted. In this case, we have this output being logits L sub I. For the private inference on neural networks, we use a library that leverages MPC with homomorphic encryption. The library computes the linear layers, such as convolution operation or fully connected layers, using homomorphic encryption, and then to compute the nonlinear layers, such as ReLU or max pooling, the answering parties engage in secure, in this case, two-party computation with the querying party. So here, because we have this joint computation of the value through one of the answering parties, the answering party engages in this 2PC with the querying party in each case. Next, we blind the individual results from an answering party. So each answering party generates a random vector R sub n, and then subtracts it from the encrypted logits L sub n. So this is possible thanks to the properties of homomorphic encryption. We want to blind the logits because otherwise the querying party would learn prediction of each answering party on all the queries, which could cause model leakage from answering parties to the querying party. So this is also to prevent what we discussed in the previous lecture, especially in this case, stealing of the model from the answering party to the querying party. In step 1b, we send the mask logits to the querying party, and then the querying party decrypts the message to get masked logits in a plain form. Then in step 1c, the querying party and the answering parties engage in secure two-party computation to compute an argmax of the logits. And this is the predicted label by the answering party expressed as a one-hot vector. So they split the one-hot vector into shares S and S hat. The S shares are returned to the querying party, and the privacy guardian receives the S hat shares. In the second step, we use a differential privacy mechanism to provide privacy for the data on which the answering parties train their models. The privacy guardian sums its S hat shares from each of the answering parties and adds the Gaussian noise by the Pate framework. At the same time, the querying party sums its S shares. Then we sum the shares from the querying party and the privacy guardian. The result is a noisy histogram of the number of votes for each class. So we obtain the histogram by adding the noisy one-hot vectors. For illustration, here we have two classes and have to decide if a given patient is healthy or has a cancer. So we take the noisy argmax and on this vote count and then return, in this case, the class being healthy. Finally, this class, healthy with maximum number of votes, is returned to the querying party as the predicted label. So the labeled query can also be used to retrain the querying party's model. And you have to here note that this decrypted label is visible only to the querying party and not to any other collaborator. So now, what is the performance of the Capsi framework? So in this experiment, we investigate the situation in which different answering parties have models with different types of architectures. So here we use, for example, VGG7, ResNet 8, as well as ResNet 10 architectures. So first we plot the per class accuracy for the model in the querying party, and this is before running the Capsi protocol. There are, in this case, 250 collaborating parties, and we set the maximum privacy budget to 2, so epsilon equals 2. The delta is set to the inverse of the data points, in this case, in this SVHN dataset. We assume that the data is uniformly distributed in each of the parties. The overall accuracy gain after running Capsi is about 2.6%. Thus, Capsi enables the collaboration between parties that have models with different types of architecture, and then helps to improve the accuracy of the models in each of the collaborating parties. In Capsi, the querying party can send a limited number of queries to the answering parties due to constraints on privacy leakage. Thus, the querying party has to select which data points from its unlabeled private dataset should be sent for prediction. The querying party decides which data samples to send at every single step in the Capsi protocol, and which data point to send to the answering parties for labeling. And here, to improve this process, we harness active learning, which is a method that selects what are the best queries to be sent to improve the local model as much as possible. So we assume that we are given an enabled dataset D and conditional label distribution. So here for a given data point X and a label Y, we just see what's the probability of this label being returned, where X is some data point from the querying party unlabeled data. So here, similarly as we also discussed in model stealing, we can use different methods how to select the best query to be answered by the collaborating parties. And here, this operation happens on the local model that a given party wants to improve. So one of these methods can be, for example, margin sampling method. So intuition here is again that the smaller the probability gap between the most probable class and the runner-up, so the second most probable class, the more information can be provided by labeling this sample for the querying party. So querying party wants to really maximize the final improvement from the collaboration and can harness different active learning methods locally to improve the local model. Apart from using margin sampling, we can also leverage these entropy sampling methods. So intuitively, we select the sample whose probability distribution is closer to the uniform distribution. So in this case, the querying party's model does not really know what is the correct class for a given example. So on the other hand, if the distribution of the probabilities of classes for a given sample is close to a deterministic 1, then this class is dominant, and probably this querying party doesn't really have to send this query to other parties because this case is simple. So, which means that in this case we know what is the label for the correct class, what is the label or correct class for a given sample, and as a querying party we don't send this query to collaborating parties. So we can do something like pre-filtering of which examples to send to collaborating parties before we engage in the collaboration. So in this experiment, we want to analyze how Capsi can improve balance accuracy. The balance accuracy is defined as an average of recall scores obtained per class. So in principle, it captures the utility of the model when the dataset is unbalanced. we consider a case when there is a skew of the initial training data in the querying party. So here classes 1 and 2 are underrepresented. So to give you more intuition about what's balance accuracy, let's just see an example. So this is a simple example of the computation of balance accuracy. So we have two classes, in this case face and place. So the face was predicted correctly 9 times and incorrectly just 1 time. Place was predicted correctly 7 times and incorrectly twice. Then the accuracy is just the number of correct predictions, so which is 9 plus 7, over all the predictions made, which is 9 plus 1 plus 2 plus 7. So the balance accuracy, so here the accuracy is just computed easily, standard way. And then how do we compute balance accuracy? So balance accuracy is focused on the per class performance of the model. So here we compute for a given class how many predictions were correct over all predictions for a given class. So here, to give you example, for the face, we had 9 correct predictions over 9 plus 1 predictions for face. And for the place, we had 7 correct predictions, and we divided by 2 plus 7 predictions made for the class place. So here the balance accuracy actually is slightly lower than regular accuracy, which actually expresses that the model does not behave equally well on all of these classes. In the extreme case, what might happen is that our classifier is perfect for a single class that might have a lot of support, meaning many examples, but this classifier might, for example, mispredict always for other class that might have, for example, small number of examples. And then the balance accuracy would be only 0.5, expressing that this classifier is not good for a single class. However, if you have many test samples for the class that is easy to compute and very few samples for the class that is difficult to compute, then accuracy would be very high and, for example, close to 1. So with this example, we see that with balance accuracy, we can focus on all the classes at the same time. So we take into account how the model performs per class and not overall on all of the classes. So first, we observe that Capsi with different sampling methods increases the overall balance accuracy of the querying model, and here by about 5.7%. Next, we zoom in one of these examples that we have underrepresented classes 1 and 2. So we see that the entropy and margin sampling methods increase the balance accuracy of these classes more than the baseline, which is a random selection of samples. And this is because the less represented classes, 1 and 2, they have a lower margin or higher entropy scores, and these samples from these less represented classes are selected more frequently for the answer by the collaborating parties. So what's intuition here is that probably a querying party does not have this example, so does not really know what is the correct class for this kind of patients, but the other collaborating parties, they had more such patients, and they can help this querying party to improve the performance on these two underrepresented classes 1 and 2. So in general, Capsi can significantly improve the fair performance of models, as here measured by the balance accuracy, especially when combined with active learning. Thus, what we discussed was how to provide data confidentiality with private inference via homomorphic encryption and secure multi-party computation. Second, we also showed how the noisy aggregation of labels provides privacy for training data in the answering parties. And now, to recap this lecture, we'll compare Capsi versus federated learning. So in terms of the final outcome, Capsi improves local models in each party, while federated learning trains a shared model and then wants to improve this global model that can be then used by all the collaborating parties. In Capsi, we can use heterogeneous models, so each party might have different model. For example, one party can have neural networks, other party can have decision trees, and still with these different heterogeneous architectures of models in each party, Capsi can help to improve local models in each party. However, this is not possible in federated learning, where we have to ensure that all the collaborating parties have exactly the same architecture of the model, so that we can aggregate the gradients. And now, Capsi also requires fewer parties over privacy. So Capsi, for example, can operate with hundreds of parties, and usually for federated learning, we have to have many more parties to ensure privacy. Capsi returns labels, while federated learning operates on the gradients. In Capsi, there is no central party, so we don't have a central party that can orchestrate the whole protocol. In federated learning, what we saw is that we can also have similar setup, for example, as in peer-to-peer learning, where we can have, instead of just collaborating parties and a single server, we can have committee, which aggregates the labels, and committee is actually selected randomly from the collaborating parties. And now, while this peer-to-peer setting provides confidentiality, and also it is doubly robust against malicious clients as well as malicious servers, it was lacking the strong privacy guarantees. And then with Capsi, we're able to provide these strong privacy guarantees and then show that it can protect for a given party its private data for the querying party using homomorphic encryption and MPC. And then we also showed that we can harness, for example, Patay framework to prevent privacy leakage from the answering parties. With that, thank you for your attention. You can further read the following papers to delve deeper into this topic. And with that, thank you very much for your attention.